All right, let's jump into fluid mechanics. We've got these textbook excerpts ready to break down the basics and unearth some seriously cool stuff.
It's interesting when we talk about fluids, it's not just like water in a glass, it's air, honey. Even the slow creep of
He's
glaciers.
like everywhere you look, right?
Exactly, and even a rocket blasting off. So much is governed by fluid mechanics.
Wild. Okay, before we go too far, what exactly makes something a fluid?
Well, most people would say it's something that flows, right? But think about squeezing, say, a block of wood. It pretty much stays the same shape.
Right.
But like a balloon full of air, you squeeze that, it totally changes shape. That gets at the difference between a solid and a fluid.
So it's how easily it changes shape.
Exactly. A fluid will continuously deform under any stress, no matter how small. Think about spreading butter on toast. That's a classic example.
Okay, yeah.
You apply a little force with the knife, the butter smoothly spreads out. It can't resist that shearing force. That's what defines a fluid.
That makes sense. But even fluids themselves, they flow differently, right?
Right.
Like honey's way thicker than water.
You're right, and that's where we get into viscosity. Basically, it's a measure of how much a fluid resists flow.
Okay.
So water, low viscosity, it's like smooth skating. Honey, high viscosity, it's like trudging through mud.
So the higher the viscosity, the slower it flows.
Precisely. And most of the common fluids we think of, like water, air, their viscosity stays pretty constant. No
Oh.
matter how much force you apply, they behave in a predictable way. We call these Newtonian fluids.
But then there are those, what they call non-Newtonian fluids, the ones that do all those weird, unexpected things.
Oh, absolutely. Those are the fun ones. They don't follow the rules. Their viscosity can change depending on the force you apply.
Right.
Like ketchup. Everyone's experienced that. You hit the bottom of the bottle, suddenly it flows easier. That's shear thinning. The force actually decreases its viscosity.
So harder you push, easier it flows. That's
Yeah.
wild.
Exactly. Then you've got the opposite, shear thickening. Quicksand is the classic example. More you struggle, the thicker it gets, harder to escape.
Yikes. Good reason to stay calm in quicksand. So we've got Newtonian, non-Newtonian. Any other types?
Well, there are also Bingham plastics. These are interesting because they act like a solid until you hit a certain force, then they flow like a liquid.
Okay.
Mayonnaise is a good example. Holds its shape in the jar, but you put some pressure with the knife, spreads out easily.
That's cool. All right. So we've got our fluid types down. What about their properties? How do we measure and make sense of how they behave?
Well, one of the most basic properties is density. How much mass is packed into a certain volume?
Right.
So something like mercury, super dense, it feels heavy for its size. Air, not very dense at all.
Makes sense, but it's not the only thing that matters, is it?
Nope. There's specific weight, too, that
Yeah.
factors in gravity. So it's not just mass. It's how much a certain volume of fluid weighs. And then you've got specific gravity, which compares a fluid's density to that of water.
Oh.
So it's kind of a quick comparison. Like mercury is 13.55 times denser than water. Gives you a good idea of how heavy it is relatively.
Right. Now, what about gases? They seem to behave differently from liquids in a lot of ways.
Oh, yeah, absolutely. Gases, they're highly compressible. You can squeeze a lot into a small space, like filling a bike tire. You're forcing all those air molecules together.
Right. Wouldn't work with a liquid.
Exactly. And that's why we need something like the ideal gas law. It explains how pressure, temperature, and volume of a gas are all related. And this is where it gets really cool because it helps us understand everyday things. Like, ever notice your bike tires feel harder on a hot day?
Actually, yeah, now that you mention it.
It's the ideal gas law. As temperature goes up, the air molecules in the tire move faster, they collide more with the tire walls, and that means higher pressure. So same amount of air, but the tire feels harder.
Huh. Never thought of it that way. Okay, so the ideal gas law helps us with how gases behave in different conditions. Any, common misconceptions about it?
Definitely. People forget about absolute pressure. The ideal gas law only works with absolute pressure, measured from a complete vacuum.
Right.
But what we see on gauges, that's gauge pressure relative to the atmosphere. So if your tire gauge says 30 psi, the absolute pressure is actually 30 psi plus atmospheric pressure.
So if I had two scuba tanks, one at 50 psi and one at 100, the one at 100 doesn't actually have twice the air.
Exactly. Common mistake. You got to factor in the atmospheric pressure to get the real amount.
Good to know. Okay, so we've got density, specific weight, ideal gas law. What other important properties should we be thinking about with fluids?
Well, we've talked about how fluids flow, but what about how fast disturbances travel through them? That's where the speed of sound comes in.
Speed of sound. So, like, it's different in different fluids.
Absolutely. Depends on how compressible the fluid is. So a disturbance can travel faster through water, which is less compressible, than through air, which is more compressible.
Ah, that's why sound is so much faster underwater. Remember learning that in physics.
Hmm.
How do we actually measure the speed of sound, though, in different stuff?
Well, for gases, there's this neat equation that relates the speed of sound to things like the gas constant, the absolute temperature, and what's called the specific heat ratio. Basically, it tells us that as the temperature of a gas goes up, sound travels through it faster.
So on a hot day, sound moves faster through the air. That's pretty cool.
It is. And this difference in speed is what we capture with the Mach number. It's a ratio that compares the speed of an object to the speed of sound in the fluid around it.
Okay.
So Mach 1, you're at the speed of sound. Mach 2, twice the speed of sound. It gets really important when we talk about things like supersonic flight.
Makes sense. So if a jet was flying at a constant speed, its Mach number could actually change depending on the air temperature, right? Since you said speed of sound changes with temperature.
You got it. A jet flying at the same speed, it would have a lower Mach number at higher altitudes where the air is colder. That's because the speed of sound itself is lower in colder air.
Makes sense. So the Mach number gives us a way to think about speed relative to the speed of sound in whatever fluid we're talking about. It's like a speed limit for that specific fluid.
Exactly. Super important for engineers designing everything from aircraft to rockets, even high-speed trains.
This is getting pretty complex. So we've covered density, specific weight, the ideal gas law, the speed of sound. It's wild how many things affect how fluids behave.
It really is. And we've barely scratched the surface. There's so much more to explore.
This is already mind-blowing. But before we move on, anything else about viscosity we should understand? We touched on it before, but it seems like there's more to it.
You're right. There's this other important idea called kinematic viscosity. It's basically the ratio of dynamic viscosity, which we talked about earlier, to the density of the fluid.
So you're adjusting for how dense the fluid is.
Exactly, because a denser fluid might resist flow more, even if its dynamic viscosity is the same as a less dense fluid.
Okay, so this kinematic viscosity gives us a more complete picture.
Exactly. It's really important in analyzing fluid flow because it helps us understand the balance between the viscous forces, which resist flow, and inertial forces, which tend to keep things moving.
So it's like finding the balance between stickiness and momentum, right?
Got it. And kinematic viscosity pops up in a lot of important dimensionless numbers that engineers use. Like one of the most famous ones is the Reynolds number.
The Reynolds number, I remember hearing that in my physics classes, but I can't quite remember what it tells us.
Well, the Reynolds number, it's kind of a rock star in fluid mechanics. It's a dimensionless quantity that helps us predict whether a flow will be laminar or turbulent.
Laminar versus turbulent, right? I remember that now. Laminar flow is smooth and orderly, like a calm river. And turbulent flow is chaotic, unpredictable. It's like the rapids in a river.
Perfect analogy. And the Reynolds number helps us figure out which type of flow we're likely to encounter.
So a higher Reynolds number means a higher chance of things getting turbulent.
Exactly. It's a super powerful tool for analyzing and predicting how fluids will behave.
Okay, so we got dynamic viscosity, kinematic viscosity, and now this all-important Reynolds number. Is that the complete picture when it comes to viscosity?
Almost. We also need to remember that viscosity changes a lot depending on temperature. Liquids usually become less viscous as temperature increases, while gases become more viscous.
Oh, right. I remember seeing those graphs in the textbook.
Yeah.
So heating up honey makes it flow more easily, but heating up air actually makes it thicker.
Exactly. And that comes back to those fundamental differences in molecular structure and how the molecules behave that we talked about earlier.
This is a lot to take in. We've gone from defining what a fluid even is to talking about some pretty complex properties. Anything else essential we need to cover before moving on?
Well, we've talked about how fluids behave under pressure, but there's another big idea we need to explore. Buoyancy. Why do some things float and others sink? How do we actually calculate those forces?
That's a great point. It seems like a fitting topic for our next segment. Stay with us as we delve into the fascinating world of buoyancy.
You know, it's pretty amazing how all these properties play out in the real world. Take surface tension, for instance. It's not just about bugs walking on water.
Right, like there's this invisible film on the surface.
Exactly. And it has all these surprising effects. Think about something like an oil spill.
Oh, yeah.
One of the factors that affects how it spreads is surface tension. It's this balance between the oil wanting to stick together and the forces that are trying to spread it out.
So if the surface tension is higher, the oil is less likely to spread.
Precisely. And surface tension is also why small droplets of liquid form those perfectly round shapes. It's all about minimizing the surface area to kind of reduce the energy tied up in that surface tension.
Like those little beads of water you see on a freshly waxed car, yeah. They just sit there, perfect spheres.
Exactly. And here's another interesting thing. The pressure inside a droplet is actually higher than the pressure outside. And the smaller the droplet, the bigger that pressure difference.
Wait, so there's more pressure inside a tiny raindrop than, say, a giant soap bubble. That's wild.
It is. And that pressure difference is a direct consequence of surface tension. It's always trying to pull that surface inward, which creates that higher pressure inside.
Okay, my mind is officially blown. So surface tension is behind everything from oil spills to how tiny water droplets form. These little forces have big effects.
They really do. Now let's switch gears a bit and go back to the speed of sound. We touched on it earlier, but I think it deserves a bit more attention.
Okay, so we know sound travels faster in water than air because water is less compressible. But why is the speed of sound so important in the big picture of fluid mechanics?
Well, think about something like a jet plane flying at supersonic speeds. The air itself is moving incredibly fast.
Right.
As that plane gets close to the speed of sound, the airflow starts to act really differently. You get shock waves and all sorts of crazy phenomena.
Right, like sonic booms, that loud boom you hear when a plane breaks the sound barrier.
Yeah.
So understanding the speed of sound, that's key for designing things that move super fast through fluids.
Exactly. And this is where the Mach number comes in. It's a ratio, compares the speed of something to the speed of sound in the fluid around it.
Right.
So Mach 1 means you're traveling at the speed of sound. Mach 2, you're going twice the speed of sound, and so on.
So if a jet is flying at, say, a constant speed, its Mach number would actually change depending on the air temperature?
Right.
Because we talked about how the speed of sound itself is affected by temperature.
You got it. A jet flying at the same speed would have a lower Mach number up at higher altitudes where it's colder. That's because the speed of sound is lower in colder air.
Right, right. It all connects.
Yeah.
So the Mach number, it gives us a way to think about speed in relation to the speed of sound for any fluid.
Precisely. And it's a crucial concept for engineers when they're designing all kinds of things. Aircraft, rockets, even high-speed trains.
Makes sense. So we've got speed of sound, Mach number. What else should we understand about how disturbances move through fluids?
Well, there's this really interesting phenomenon called cavitation that can happen when the pressure in a liquid drops below its vapor pressure.
Cavitation. I've heard that term before, but I can't quite remember what it is. Isn't it something that can be damaging to machinery?
You're right. Cavitation is basically when vapor bubbles form and collapse in a flowing liquid. It happens when the pressure drops low enough, and then those bubbles implode with a ton of force.
So like tiny explosions inside the liquid.
Exactly. And those implosions, they can create shock waves that actually erode metal surfaces. They can cause a lot of damage in things like pumps, turbines, all sorts of equipment.
Wow. So engineers have to be very careful about this when they're designing systems that involve fluids moving at high speeds or under changing pressure conditions.
Absolutely. Understanding cavitation is crucial to preventing damage and keeping fluid systems running efficiently and reliably.
It's fascinating how something seemingly so small, little bubbles forming and collapsing, can have such a big impact.
It just goes to show fluid mechanics is full of surprises. Even the smallest change in pressure or temperature can have these huge effects.
Okay, so we've explored surface tension, the speed of sound, and now cavitation. What else is there to know about this incredible world of fluids?
Well, let's go back to our conversation about buoyancy for a bit. We mentioned Archimedes' principle earlier, but there's so much more to unpack when it comes to understanding why things float or sink.
Okay, so Archimedes figured out that the buoyant force on something is equal to the weight of the fluid it displaces. But how does that actually explain why, say, a huge ship made of steel can float while a tiny pebble sinks?
Well, it comes down to density and the shape of the object. A ship, even though it's made of dense steel, is designed to displace a huge amount of water. That large volume of water being displaced creates a buoyant force that's bigger than the ship's weight, so it floats.
So it's not just about the weight of the thing, it's about how much water it pushes out of the way.
Exactly. Think about a beach ball. It's filled with air, so it's very light, but it displaces a lot of water relative to its weight.
Right.
That creates a big buoyant force that easily overcomes its weight and makes it float.
Okay, so the shape and design of something plays a huge role in whether it floats or sinks. But what about submarines? They can float on the surface and dive deep underwater. How do they manage that?
Submarines are a great example of how we can actually control buoyancy to change an object's depth. They have these tanks called ballast tanks that can be filled with either air or water. When they're full of air, the submarine is less dense than the surrounding water, so it floats on the surface.
So it's like a giant metal beach ball, basically.
Exactly. But when the sub needs to dive, it fills those tanks with water. That makes it denser overall, causing it to sink. And to resurface, the water is pumped out, air replaces it, and the submarine becomes less dense again, rising back up.
Wow, that's so clever. It's like a carefully controlled balancing act between density and buoyancy.
It is. And it's a perfect example of how we understand fluid mechanics and can use these principles to build amazing things.
So buoyancy isn't just about whether something floats or sinks. It's about understanding how we can actually control where something sits in a fluid by changing its density and the amount of fluid it displaces.
Precisely. And this principle applies to all sorts of things. Ships and submarines, but also hot air balloons, blimps, even those underwater ROVs, remotely operated vehicles.
It's amazing how we use buoyancy to explore the world around us, both above and below the surface.
It really is. And it all comes back to those fundamental principles of fluid mechanics we've been discussing. It's amazing to see how these seemingly simple ideas lead to such complex and incredible applications.
Okay, I think we've covered a lot of ground here. We've gone from surface tension and the speed of sound to cavitation and buoyancy. Fluid mechanics is a field full of surprises and just endless possibilities.
It really is. And we've only scratched the surface. There's so much more to learn and discover.
This has been an awesome journey so far.
Yeah.
But before we wrap up, there's one more thing I want to get into. The whole idea of fluid flow. How it affects everything from weather patterns to the way we design airplanes.
That's a great point. Understanding fluid flow is key to understanding so many things.